So before we start, I wanted to remind you that the conference T-shirts are still for sale, and with a special bonus that if you buy now, you might get one of these for free. This is the 2014 edition of the first conference, and I have a bunch left over that has nothing to do with. So if you bought a T-shirt already and you want to see if there's a size for you, go ahead. If you buy one now, you can also try to get one of these for free. Okay? All right. So it's my pleasure to introduce David Cox, the professor at Amherst College, and he's very well known for his expositions. He's an excellent writer. He's he was awarded the Lester Ford Prize from the MAA in 2012 for his article "Why Eisenstein Proved the Eisenstein Criterion and Why Schoenemann Discovered It First." He's also awarded this year himself, Little and O'Shea. They were awarded the AMS Steele Prize for exposition for their book Ideals, Varieties, and Algorithms. He's a fellow of the AMS. And in his website you can find there's a lot of lecture notes that are amazing. And he's written a bunch of books, but he's written one of these books that I think will be an instant classic, and a classic for the rest of the time. A timeless classic. The book Primes of the Form x squared plus n y squared. It's just an amazing book that should be in everyone's bookshelf. So anyway, David Cox will be talking about Gauss and the arithmetic-geometric mean.
Thanks, Alvaro, for the introduction. I'm really pleased to be here to tell you about some fun stuff. So I'm going to talk about these two topics. I'm going to do the arithmetic-geometric mean first. And so, I'll define it, discover that it's a pretty simple object. It has a relation to elliptic integrals. It gets really interesting when we go over the complex numbers, and it also ties into stuff that you're actually playing with this sum. So that's going to be sort of the math part of the talk, and we will get to do some really interesting, fun stuff. But then I'm going to talk about Gauss and see what role he played in all this stuff. We'll say a little bit about his mathematical diary. There's something that Gauss called a most important theorem. We'll see what he thought about that. We'll look at some fundamental domains the way that Gauss drew them. That's something that you've been studying this summer. And also just read part of a letter that Gauss wrote to Bessel in 1828 to sort of give his take on what he had thought. So to get started, we're going to take two positive real numbers, a's or equal to b, and then take these two numbers, you get the arithmetic mean. That's just the average of the two numbers. Call that A1. And it's sort of the number that's halfway between A and B in the sense of addition. But there's also the geometric mean, which is the square root of AB, and that's sort of halfway between A and B in the sense of multiplication. But the thing, and then of course there's the famous arithmetic mean, geometric mean inequality. Basically says that the arithmetic mean is always greater than or equal to the geometric mean. That's a little bit of easy algebra that you can do. So what that means, if I start with these two numbers, AB, I get two more numbers, A1, B1, that satisfy the same inequality. So it makes sense to iterate. So here's an example of what happens when we iterate. So I started off with A, so I think of A is A naught, B is B naught. So that's I'm starting with that number and that number, and then I just do this little process. There's the arithmetic mean, there's the geometric mean, and notice that they start sort of looking similar. In fact, by the fourth step, the only place they differ is in these decimal places. There's a 41 and a 39 there, otherwise they're the same. So somehow this process converges like really fast with the same thing. So the two things I want to say about this example is I didn't do this example. Gauss did this example in 1799 without a computer. And the other one is, anybody recognize what that number is? Square root of 2. And we will see later in the talk that the ability to look at a decimal and recognize the number is actually significant in what's going on. So that's an example of the arithmetic-geometric mean. And so it turned out there's some very easy little theory that works behind this. And so, for example, so here's this, again, take our setup, and again, you initialize, A naught, B naught, and then AN plus 1, BN plus 1 is going to be, the arithmetic mean and the geometric mean of the previous pair. And I've written that here on the board because in case I want to refer to it later in the lecture. And then the theorem you can prove is that, so here's A, here's B, and then the point is that when I do this, the arithmetic means, so basically they go this way, the geometric means go that way, and so those are sort of going toward the middle, and the difference between these guys, so that difference right there, it's basically, it depends on how far apart A and B were, of course, but basically it decreases exponentially. And so notice that, so you really do have this common limit, so that explains, what we saw in the previous slide about, looks like we're getting to a common limit. And then, of course, the fact that, this exponential decay, that sort of explains why we're getting here, like, really fast. So that's very satisfying. It's a very nice setup that we have. And so this is the definition, because it's built out of the arithmetic mean, the geometric mean. We'll call this the arithmetic-geometric mean, and we call it AGM for short. And basically, MAB is simply, the common limit of these two sequences. So that's the arithmetic-geometric mean. And then here's two very simple examples. Of course, if I take a number in itself, well, if I take the two numbers the same, well, the average is the same, the geometric mean is the same, so I just get two constant sequences, and so of course, so we get that one, and then of course in this case, here's the other one that we have done before. So far it looks really simple. Now our first hint that there's something interesting going on is this theorem. It says if you take the arithmetic geometric mean and multiply it by this funky integral, which also depends on A and B, then you always get pi over 2. And so let's prove that. And so I'm going to let the integral, I'm going to dump the integral by I of AD. So I of AD is that integral right there. And I'm going to introduce a new variable phi prime, and phi prime is related to phi by this little obvious equation. You look at it, oh, obviously that's the change variable. And then it turns out that when phi goes between 0 and pi over 2, phi prime does the same. So we're going to be dealing with the same range of angles. And then after the development has been made correctly, it can be seen that. So basically, if you do a lot of work, you get this kind of answer. And so notice what happens is that, here's the stuff with the square root for the original one, but notice what's here for the new variable, I've replaced it with A1 and B1. And so what that means is that when I integrate this from 0 to 2 pi, that's the same as integrating this from 0 to 2 pi. That means the interval here for AB, it's unchanged when I replace A and B with the arithmetic and geometric means. But then I can iterate that. And then, of course, if I iterate that, we'll actually get a limit. And to take the limit actually inside the interval, you have to use little uniform conversions, but that's easy to prove. And so the point is these guys converge to the exact same thing. And of course, this common limit is, of course, the arithmetic geometric mean. So when I keep iterating, the limit I get back. But of course, the integral here is just, well, that's where those guys are the same. But that, you see, I can factor out. Cosine squared plus sine squared is 1. You basically get 1 over mu here, integrating between 0 and pi over 2, so you get back. And so you get that this integral is pi over 2 times mu with the denominator, and then when you clear the denominator, you get exactly 0. So it's a very nice, easy, simple proof. But when you do it this way, like I said, lots of instructor under the rug here, but not just basically calculations. So this is nice, but to get a sense of what's really going on is we realize this is actually the integral. Because if you make this little substitution here, it turns out that this integral in terms of z, the range of integration is 0 to 1, and then if the d phi is it's basically dz over that square root, and then this stuff turns into that. and notice that's the square root of a coordinate, and it turns out that that's an elliptic curve. Now you're probably studying elliptic curves where you have w squared equals some cubic, and that's a more common form these days, but it turns out that the way elliptic curves first arose historically were in cubics. And in fact, one particular example is if you let a be the square root of 2, and b be 1, you get this elliptic integral. Then when you make the little switch here, you get that. And it turns out that is the first elliptic integral that's ever written down. It was done by Bernoulli in 1691. And it turns out that Bernoulli was doing a lot of stuff. And it turns out that this integral was so well known, it actually had a name. And of course, if you replace that 4 with a 2, you get the integral from 0 to 1 of dz over the square root of 1 minus z squared. Does anybody know what that integral equals? Let me write that down. So this is a second semester calculus. So what's that guy?
I over 2.
I over 2. And so what they did is, and then they sort of knew that this was sort of somehow vaguely related to each other. And so what they did, so Library gives pi over 2. So here they use this funky thing, and it turns out that's a variant of pi. It looks like an omega with a bar over it. I'm going to call it pi tilde. So this is denoted pi tilde over 2, again because of the analogy with that classical thing. But it turns out that, because pi over 2 also, if you think about it, it's, when you look at the circle, it's basically the first quadrant arc length of the circle. And so there's your pi over 2 right there. Well, this one, instead you use the lemniscate, and it's the first quadrant arc length of the lemniscate. And of course, the lemniscate was actually also invented by Bernoulli. And also, just for fun, it turns out that Bernoulli actually invented polar coordinates so he could sort of, compute the arc length. So a lot of fun stuff happened in 1691. And of course, when you think about calculus, you'll probably learn about the lemniscate. You might learn about arc length, but of course you'll never compute the arc length of the lemniscate because it gives an elliptic integral. And so even though this stuff was there at the birth of it, calculus is, he sort of ignores the interesting stuff as usual. But then if you combine this with our theorem, well, remember that, when you look at our theorem, that basically says when you do this, that turns it into this guy. And so when you have the theorem from the previous slide, this guy, and right here, we're going to basically get, when I put the square root of 2 and 1, I'm going to get here, I'm going to get basically omega tilde over 2. And so when you sort of do the little bit of algebra, you discover that the arithmetic-geometric mean of the square root of 2 and 1, which we had computed before, is actually pi over pi tilde. So that little, seemingly harmless computation, all of a sudden, there's pi, there's the arc length of the lemniscate. So there's something interesting going on. So let's have some more fun. Talk about a few more properties, because it turns out that you can actually turn this formula on its head in an interesting way. And so, because of course here's one property, because of course it's sort of a homogeneity property. If I multiply a and b by a constant, well basically I can pull that constant out, and because it basically just multiplies the arithmetic mean by lambda, it multiplies the geometric mean by lambda, and so you get that it just multiplies the whole arithmetic geometric mean by lambda. And also, if you take the arithmetic geometric mean of these two guys, you'll notice that the average of these two guys is just a, and then the geometric mean, again, it's the square root of the product, is that. And so if you let c just be that, square root of a squared minus b squared, then you get that. And So it turns out that what you can do is you can take our usual AGM sequences. Here I'm going to do a little variant. Instead of taking the square root of 2 and 1, I'll take 1 and 1 over the square root of 2. It makes it a little smaller. And then for these sequences, I define the CN sequence that comes from this. And it turns out that using the properties of elliptic integrals, you can turn all this stuff on its head, and you actually get a formula for pi in terms of the arithmetic-geometric mean and the C sequence. And of course, right here, again, I can use this homogeneity to, multiply through by the square root of 2. And so there's our friend, the arithmetic-geometric mean of the square root of 2 and 1. You throw in the CN squareds, and you get basically pi. And remember that this guy converges really fast. And so this is actually a useful formula for pi, and people have used this formula and its variants to compute pi to a billion decimal places. And so what we discover is that not only is this guy implicated in the arc length of the lemniscate, you can actually use it to help you compute pi. So this is a very fine number that we have. But it turns out that things get really interesting when we play this game with complex numbers. Then a whole new thing emerges. Because, so I can take two complex numbers, I can play my same game, I can start by iteration, and then, I can, take my two complex numbers. Of course, the complex numbers are algebraically closed, so I take the product of the two, I can take the square root. The problem is, I get two choices for the square root. Now notice that when I try to do this geometric, this AGM game, basically at every stage, there's a choice of two things. So I have countably many choices between two things. That's uncountable many. So for a given start, AB, I get uncountably many AGM sequences. So that's looking a little weird. But it turns out some of them are pretty nice. So for example, I'll just start with 3 and 1, just real numbers. And then again, there's the average, the arithmetic mean. But for the geometric mean, let's make the wrong choice. So instead of using just the square root, because that's of course the square root of 3, but let's take the minus square root. So what effect does that have? Well, again, for these two numbers, I take their average, it's that. But then I take their product, the product is a negative number, take the square root, all of a sudden I have an imaginary number. And then, of course, I continue on. But notice it still seems to be convergent, because they're the real parts seem to be the same up to that. And then here, that's an 8.5 and an 8.8. So it still seems to be convergent. So maybe there's something here. And so the question is, what happens when you actually play this game with complex numbers? So what kind of things can actually arise? So it turns out that what happens is that there's actually a right choice you can make. At any stage of the game, there's a best choice that you can do. And so to make sure we don't run into any awkward things, I'm going to take my two complex numbers. I'm assuming they're non-zero, and I'm assuming that neither is plus or minus the other. And so then I take one of these AGM sequences. And I say that Bn plus 1 is the right choice. Because remember that, suppose I have An and Bn. See, if I have An and Bn, then An plus 1 is guaranteed. But then you see for Bn plus 1, I may take the square root. There's two possibilities for Bn plus 1. If I call one Bn plus 1, the other is minus Bn plus 1. And remember that I want these sequences to converge. I want these guys to be getting close, and so if there's two choices here, it makes sense that the one I like is the one that's closer to that guy. And so that's what we're going to do. So I can say that's the right choice if among these two ones, this is the one that's closest to that. And then also we have to break ties sometimes, because of course if those two numbers, if that's an equality, I still want a way to decide it. And there, it turns out I just look at the imaginary part of the ratio, and then that'll determine things for me. And then I say that these two sequences are good sequences if Bn plus 1 is the right choice for all but finitely many n. So I give myself permission to make finitely many bad choices. So I can mess up, a billion times, but at some point I got to stop, and after that, it's always got to be the right choice. Now, the impact that has is that what happens is I'll have uncountably many of these sequences, but it turns out there's only countably many good ones. So that's looking a little more hopeful. So maybe there's something interesting going on. Because again, our basic question is, first of all, do the two sequences converge the same thing? And second, is the thing they converge to interesting? So that's the two kind of questions we want to answer in this complex case. We certainly saw good evidence in the real case that that common limit is an interesting thing. So what happens in this complex case? So here's the theorem. So the first theorem says that, so first of all, let's just take any of these uncountably many AGM sequences. So like I say, arbitrary one. I have permission to make as many bad choices as I want. And it turned out they always have a common limit. So all of these uncountably many sequences always converge to the same number. Turns out that most of the time that number is sort of boring. Namely, it's the number 0. And so what happens is the common limit is a non-zero number. See, this is where these hypotheses come in. The common limit is non-zero if and only if these are good sequences. And what happens is that what you can do is you can prove that every time you make a bad choice, basically things get small. And so if you make an infinite number of bad choices, basically that's going to force the sequences to converge to 0. Now that's sort of the intuition behind the proof. So that's pretty good. So what that says is that, okay, we've got a situation where we really want to focus on these good sequences. And so we're going to have these, basically out of countably many non-zero complex numbers. And I claim they're interesting. And so let's give some definitions. So first of all, the values of the arithmetic-geometric mean are the common limits of the good sequences. And so again, basically for complex numbers, there will be countably many of these common limits. But it turned out that one is nicest. I'll call it the simplest value, because one thing I could do, of course, is always make the right choice. From the very first step, every time, make that right choice. And so I'll call that the simplest value. And so here's the theorem. So again, this is our usual hypothesis. And also, in the real case, I assume that A is greater than or equal to B, so this is a way of sort of, capturing that, the flavor of that in the arbitrary complex case. And then what I do is I take mu to be the simplest value of the arithmetic-geometric mean. And of course, we've already seen this guy sort of play a little role in the real case. And so it turns out its simplest value is also going to play a role here. And then the theorem says that all values that I get, so again, all these common limits of good sequences, are given by this formula. And so the idea is that, what I'm going to form some complex numbers as follows. So I take my two simplest values, I use those as denominators. The numerators are d and I times c, and d and c are just integers. I want them to be relatively prime. I want d to be congruent to 1 mod 4, c to be congruent to 0 mod 4. So the point is that out of these two simplest values and this collection of pairs of integers, I build basically a bunch of numbers, and those are exactly the reciprocal of all the values. So that's an astonishing theorem that somehow these sequences have this sort of internal structure that somehow relates them to each other. So what that says is there's got to be something reasonably deep going on here to force all these limits to hang together in this way. And it turned out the proof is where we're going to use theta functions, and modular forms. And so what we're going to see is there's a lot of astonishing stuff sort of working here in the background. So how do we start with that? Well, we're going to start with some theta functions. So we're going to take the upper half plane, and as usual, we let q be e to the pi I tau. Now, theta functions are very well known. I don't know if you've actually seen theta functions as part of your stuff, but they're definitely out there. This is not sort of the standard notation for these theta functions. These theta functions are very well known. This is Gauss's notation, and so I decided to use that. And it turns out that theta functions satisfy a gazillion identities. So that they just phenomenal. So for example, if I take the fourth powers of P and Q and subtract them, I get the fourth power of R. And also if I take P squared and Q squared, add them up and divide by 2, well I get P squared, but I basically multiply tau by 2. And then also, if I multiply P and Q, I get Q squared, but again, tau is multiplied by 2. But then you notice something interesting. Like, hey, here's P squared, here's Q squared. This is the arithmetic mean. So the arithmetic mean of P squared and Q squared is P of 2 tau squared. And of course, this is one of these square roots of this guy. And so, this is, so Q of 2 tau squared is the geometric mean of these two. So that says that, hey, if I let this be A and that be B, then here's A1 and here's B1. So this actually has something to do with the arithmetic geometric mean. And so here's the two consequences. So first here I just said what I sketched out. So basically if I take A and B do this, then one choice, because of course here notice that this picks one of the square roots. And so here what that says is that when I look at A1 and B1, I can actually sort of get these values right here. And then so basically, one way to think about if I start with this P and Q, then A1 and B1 are I just double the tau. And then of course, what happens is that what am I going to do when I take the arithmetic geometric mean of these two numbers? Well, the point is that every time I iterate, I just multiply by another power of 2. So I'm really just taking, 2 to the n times tau for either P and Q. But notice that these functions behave really nicely because, of course, when I multiply tau by powers of 2, I'm setting the imaginary part of tau to infinity, because I'm in the upper half plane. And so basically, when I take 2 to the n here, this function Q goes to 0. So these all go to 0, so I'm just left with 1 as the common limit. Now at this point you might be a little disappointed because you might have thought that, well, this is going to be like really important because, clearly these theta functions are deeply related to the arithmetic geometric mean, but then the arithmetic geometric mean is just 1. That's like boring. And then so the question is, how do you get something interesting out of this? Because right now, this looks like a cute fact, but it's not clear it's going anywhere. And the answer is, let's bring in the homogeneity. Because if I now, because remember you can multiply the A and B by anything, and of course when I just P of tau squared, Q of tau squared, I get 1, so if I multiply by mu, I get mu there. But now notice that I want to compute the arithmetic geometric mean of any two numbers. But the point is that, so that's two numbers, but here notice I also have two numbers. I have mu and tau. So the idea is that maybe if I pick my mu and tau really carefully, I can get this to be any pair of complex numbers. So maybe this will actually enable me to compute an arbitrary arithmetic geometry. So that's really good. And here's the way you do it, is that, so notice that one thing that happens when I look at, if I take A and B and represent it this way, if I want to get rid of the mu and just figure out what the tau is, I just take the ratio. Okay, just take basically A over B, or rather B over A. So that's just Q squared over P squared. It turns out that that's a function that's also well known from the theory of what together goes. It's called K prime. It's the conjugate modulus. And so that's a very classical kind of thing. And so given this function, I can now give you a recipe for trying to compute a value of the arithmetic geometric mean. Because first of all, what I do is I take a tau in the upper half plane such that K prime of tau is the ratio of B over A. And then I set mu equal to A over P of tau squared. So notice that this says I start with A and B, I pick a tau, and then from the tau in my A, I get the mu. And it turns out that, so notice that this equation right here guarantees that mu times P of tau squared is X, so that's guaranteed. Is this equal to D? And the answer is yes, because of course what's mu? Well, mu is just this quotient, it's that. But of course, notice that I get Q of tau squared over P of tau squared. Well, that's K prime. And of course, K prime is B over A. And so when I, so that becomes B over A, the A's cancel, and I'm left with B. So in fact, this recipe does give me a tau and a mu that makes that guy equal to A, that guy equal to B. And it turned out that follows that this mu is a value of the arithmetic geometric mean. And it turns out that when you put our usual hypotheses, basically you can prove that all values of the arithmetic geometric mean are rising this way. So we're going to get absolutely everybody. So the question is, how do we understand that? And what that means is there's two things we have to understand. We have to understand how do you solve this equation? How many solutions, how many taus, given B over A, how many taus make this work? Because you see, that's what's going to give me multiple values for this guy. Because, because once I pick A and B, if I can find lots of taus, then each tau gives me a different mu, so that's how I'm going to get my counter many mu's, the values of the arithmetic geometric mean. So we have to understand that. And then, so we have to understand how the solutions of this equation are related to each other. And then we have to figure out how P behaves on those solutions. So that's the two bits of things that we have to do. And what we're going to see is that's going to involve understanding a modular function and a modular field. And so that's going to be the language that's going to sort of unravel all this beautifully for us. So here's the modular function. So this is a modular function. The modular function, so you have the group SL2Z, that's the group you've probably been learning about most, but you have certain subgroups of that of finite index. They're called concord subgroups. Those are the nicest groups of finite index. And it turns out that this one, and basically a modular function just means it has the nice kind of properties, and it's also just plain invariant under the group action. And it turned out that in this case, the group you take is, so you take your A, B, C, D, and SL2Z, and you want modulo 4, you want it to sort of look upper triangular with ones in the main diagonal. And then also, it's also C in particular is congruent to 0 mod 4. But B, I don't want to be arbitrary. I want B to also basically be even. And so that's the matrices I want to do. And it turns out that this map, so when I take the upper half plane and mod out by the action of this group gamma 2 of 4, it turns out that that maps to the complex numbers. It omits 0 and plus or minus 1. And notice that our hypotheses on A, that A and B are non-zero and not equal to plus or minus each other. So B over A is going to live in this set. And it turns out that this actually not only maps here, this is actually a complex analytic isomorphism. So this is like really nice. And it turns out here's an example of the fundamental domain. So it's basically, it's a slightly funky one because you've seen the fundamental domain for SL2Z. It's fairly pretty. This one's a little